says a 100 milliliter sample of molarity sodium hydroxide is reacted with nitric acid if both solutions were initially at 35 degrees Celsius and the temperature of the resulting solution was 37. Determine delta H reaction in units of kilojoules per mole sodium hydroxide for the neutralization reaction between aqueous sodium hydroxide and nitric acid. Here, assume that no heat is lost to the calorimeter or to the surroundings, and that the density and the heat capacity of the resulting solution are the same as water. So this to me looks like it was a former exam question, because the exam questions are always much more well-defined than the previous question we worked, in which I told you that these assumptions were important. That looks more like a homework question. So anyway, could be a future exam question, not for exam 1, because the material we're doing today is for exam 2, because this is week 5, and the exam's only on weeks 1 through 4, and homework's 1 through 4. Your work counts for this problem. The reason your work counts for this problem is because you could literally look up the delta H reaction for nitric acid and sodium hydroxide, and you would get the same answer, because that's how I created this problem. So show all of your work to get credit. Well, here we have, so let me write your reaction for you. It's going to be sodium hydroxide. That's aqueous because it's a solute dissolved in water, plus nitric acid. And it is no coincidence that these are a strong base and a strong acid. Those are going to do a double replacement reaction to make water and sodium nitrate. And I guess the one thing that's missing, were this an actual exam question, is I would give you the balanced reaction, because I wouldn't expect you to come up with this reaction, although I think many of you could. Okay, so I have enough information, milliliters and molarity, to get moles of sodium hydroxide. I've got enough information to do the same thing for nitric acid. That means this is potentially a limiting reaction problem. However, since the volumes and the molarities are the same for both of them, this is a problem in which both of them are going to be the limiting reactant. We could prove that, but I will leave that up to you. What we need is to realize that this is a coffee cup calorimeter problem with a reaction. There's only two types, two broad types, and since this has a reaction, it will be Q reaction equals minus Q solution, where the minus sign just means that something is giving off, one of these is giving off heat, and one of these is taking heat in. I think we can figure that out. So the temperature of our solution is increasing, and that means that this is an exothermic reaction, and therefore delta H that we figure out will be negative. So let's see what we got here. Let's go ahead and write terms out. So we're going to be looking for delta H reaction. The problem specifically says moles of sodium hydroxide. That is one of our reactants. Here's our minus sign from the previous equation. But then Q for the solution is just going to equal mass of the solution times the specific heat of the solution, which is the same as water, and T final minus T initial. There's only one initial and final temperature. Those are for the solution, but I won't use my solution subscripts in order to save a little space. We know all of these except delta H reaction. Let's go ahead and pick them out of the problem statement. So our moles of sodium hydroxide, we know that we have a volume and a molarity. So I'm going to go ahead and do that right here. We have 0.1000 liters. We have 0.3 molarity, which is moles per liter. And this amounts to anything times 0.1 amounts to move the decimal point one more place over. So I get 0.0300 moles of sodium hydroxide. That's my moles there. My mass of solution, actually let's just go through the terms and figure out what we need to do. Our mass of solution, well, we know that we have 200 milliliters of solution, 200.0 milliliters, and we know that the density of the solution is the same as water, which is 1 gram per milliliter. And therefore we have 200.0 grams of solution. And this is very common, so you do have to add up the volumes of the solutions, convert them into grams, and that is always where you get the mass from. A common mistake is to think to get the moles here and turn them into grams, which I totally get because we do that so much in this class. However, it's a little different this time. And I'm happy to talk more about that if you have questions. The specific heat capacity of the solution is the same as that of water, 4.184 joules per gram degree Celsius. I think we're ready to plug everything in. Delta H reaction is what we don't know. We do know our moles of sodium hydroxide. It's 0.0300 to 3 sig figs. Our mass of solution is 200 grams. Our specific heat capacity of our solution is that of water. Our temperature final minus temperature initial is going to be 37 minus 35. That's 35.00 there. And so that's just going to be 2.00 degrees Celsius. And we've got everything except our delta H of reaction. We can now solve for it. Again, now we're off to the algebra Olympics, if you will. So multiply everything on the right, divide it by the thing on the left. We see that we have a minus sign here in all positive terms. So our delta H reaction will be negative. And that has to happen because this is, the temperature of the solution is increasing, which can only happen if the reaction is exothermic and giving off heat. So, minus 200, actually I guess I have to do my minus now, times 4.184 times 2 degrees Celsius, I get minus 1673.6 divided by 0.03. I get minus 55,786.66667. And that's way too many sig figs as it is, but I'll cut it off there. Now let's do a unit analysis to make sure we're comfortable with our units here. So my grams cancel. My degrees Celsius cancel. So therefore, the right-hand side has units of just joules. Then I divide by my moles to get joules per mole. And then we cut it down to 3 sig figs. When you do that, you can either do minus 5.58 times 10 to the 4th joules per mole, or you can convert it into kilojoules, in which case you'll move the decimal point 3 places. Oop, 3 places. The decimal point's way over here. 1, 2, 3 places, and get minus 55.8 kilojoules per mole. Either set of units are fine. Remember, I always prefer 3 significant figures. Both of those answers have 3 significant figures. And let me see. Oh, aha. this is submitted online, so it's important that we have in units of kilojoules per mole. I'm glad I remembered this when I wrote up this problem. So it does have to be kilojoules per mole. And it's at this point that I'm going to take a minute to discuss delta H reaction and its units versus Q reaction. So delta H reaction always has units of joules or kilojoules per mole. So I guess that should be colon. It's always in joules per mole or kilojoules per mole. In practice, it could be other energy per mole or energy per substance units. Engineers in particular can sometimes see joules per gram or kilojoules per gram. Now, Q reaction is a heat energy only, meaning it could be in units of joules, it could be units of kilojoules, but it will never be joules or kilojoules per mole or per gram. So this is heat for Q. Delta H is heat per amount. Where in this course, it's almost always joules per mole or kilojoules per mole, though there are other units that can be handy under certain circumstances. Any questions about this problem?
Yes, Professor, could we use the molarity in this problem because it's given?
Can we use the molarity? We did use the molarity in this problem, and we do need to, but only to find the moles to plug into our equation.
Oh, okay.
Okay. Now, there is, and that's a good question, Demith. There is a question where you also have to determine the limiting reactant. In this case, we said that the two had the same number of moles if we did the calculations. So there's one other potential step. I don't know if we're going to see it on this homework, but you could also determine the limiting reactant.
Okay, Professor, in case one reactant is limited, what will we use here to determine the mole of? Are we going to use the mole of NaOH who have reacted?
So, for example, let's say we had 200 milliliters of the nitric acid. If we multiplied that out, that would be 0.06 moles of nitric acid, in which case that would be the larger number, and the moles of sodium hydroxide would be for our limiting reactant. And that's whatever is our smaller number of moles, whichever is the moles of our limiting reactant, is what goes into this equation, because it's the actual. Remember, when I first wrote this, and this is what I did in the lecture outlines, this says moles reacted. So not moles of the excess reactant. I don't know if that answers your question.
Yes, Professor, thank you.
Yeah, I'm trying to think, because I don't think I remember seeing a problem in which you have to do the limiting reactant as well. I wonder if there will be a limiting reactant style question on next week's recitation. There may be. In fact, I think there is, if I remember, because I just put that up on Blackboard as well. Yeah.